The 1500-meter event is a mid-distance track event in athletics. The 1500-meter event is characterized by a combination of running and sprinting, as shown from the graph. Given its length and the incorporation of aerobic and anaerobic energy system, pacing is critical to the athlete's performance. Alongside this, the athlete will also need to possess a combination of speed, endurance, and the ability to cope with the intense physical and mental pressure to finish the race strong. We will have a look at these factors in more detail in the upcoming slides. In the 1500-meter run, as shown from the graph earlier, athlete tends to run at a steady pace in the first half of the event. They do this to conserve energy before the surge that occurs in the latter half of the event. Aerobic metabolism is the primary energy producer for this phase. And as we know, in this phase, oxygen plays a huge role in this part, and that we need to consider strategies in optimizing the athlete's oxygen uptake. The maximum oxygen uptake is defined to be the product of systemic blood flow and systemic oxygen extraction. One factor that has shown to affect athletes' performance is stress, whereby literature writes that stress elevates sympathetic nerve activity, and that reduces the cardiac output, thus impairing the oxygen consumption. Hydration is also another factor that influences oxygen uptake. Whilst the current literature has conflicting theories on the changes in hydration on preloading, there is a consensus on how dehydration affects peripheral resistance, which reduces cardiac output. Given this, athletes' training plans should include hydration and stress management in optimizing their performance. Outside the cardiac realm is where the metabolism occurs, the muscle. Both the aerobic and anaerobic pathways produce a high number of free radicals. Free radicals being highly reactive and can react with cellular components that can disturb muscle homeostasis, which can concurrently reduce cellular efficiency and muscle fatigue. Evidence shows that antioxidant diets can improve antioxidant capacities. However, before prescribing an antioxidant-rich diet, it is advisable to consult with the dietitian, as studies have shown that such diets can block cellular adaptation by interfering with the cell signaling pathways. In the latter half of the event, as the athlete sprints, energy is produced through the anaerobic pathway. The ATP-PC energy system relies on the body's store of creatine. However, because these stores are limited, creatine supplements have been shown to improve energy production and enhance athletes' performance. It is worth noting, however, that such supplementation is not recommended for 1,500-meter runners. The literature suggests that creatine supplementation can lead to an increase in body weight, which in turn can negatively impact run economy, a crucial factor in the first half of the event. Nonetheless, research has demonstrated that carbohydrate diets to improve performance in runners, whereby carbohydrate meals prior to event can enhance performance by increasing energy nutrient stores. Moreover, the amount of carbohydrates consumed during the training period has found to influence cellular adaptation. Therefore, it is important to tailor the athlete's diet to their training program to optimizing their performance outcomes. Just as there are differences in the energy system, there are also biomechanical differences during the 1500-meter run. Relative to a run, sprinting, that happens in the latter half of the event, requires the athlete to generate a higher vertical ground reaction force in a shorter amount of time. Sprinting also requires fast and forceful activation of the iliopsoas and hamstring during the swing phase, as well as the gluteus maximus and medius during toe-off to push the leg as far forward as possible. However, despite these differences, the muscle contraction patterns involved in producing a sprint and run are the same. We will examine the contraction occurring at each joint in the next slides. At foot strike, the foot lands supinated. The supination dampens the initial shock. Pronation immediately occurs after this and peaks at 40% of the stance phase. The pronation further attenuates force and allows the first rate to meet the ground for toe-off. The tibialis posterior, gastrocnemius, soleus, flexor digitorum longus, eccentric contract in producing this movement. During this part of the stance, the tibialis posterior controls the rate of pronation and provides dynamic support across the mid and forefoot. Weakness in this muscle can cause overpronation and alterations during coupling that can increase the stress on the plantar fascia and the Achilles tendon. For injury prevention, the tibialis posterior function should be assessed regularly. From mid-stance onwards, the foot supinates again. The supination motion increases the foot rigidity and allows the athlete to lever off from the foot for toe-off. This movement is done through concentric contraction of the gastrocnemius, soleus, tibialis posterior, peroneals, flexor hallucis longus, and digitorum longus. The ankle then dorsiflexes throughout the swing for foot clearance and placement for initial contact through concentric contraction of the tibialis anterior. At the knee, at foot strike, there is a mild knee flexion to attenuate the impact force. This is done through eccentric hamstring contraction. Synchronous to this movement, the pronation movement at the foot drives the tibia into internal rotation. This motion causes the knee to move into 4 to 6 degrees of genu valgum. The vastus muscles takes over the role from the hamstrings at around the 20% mark of the stance, and works eccentrically in controlling knee flexion up until the 40% mark of the stance, at which point the contraction switches to concentric. While the pronation produced various movements through the foot, ankle, knee simultaneously, with the supination motion, the changes are asynchronous, whereby the knee abducts first, followed by knee extension, external rotation of the tibia, and inversion of the ankle. The asynchronous motion enables the knee to work like a whip, propagating the propulsive force down the kinetic chain. All the other muscles crossing the knee joint, such as the sartorius, gracilis, popliteus, and ITB, work eccentrically and isometrically to minimize internal and external rotation at the knee in both swing and stance. The hamstrings reactivates concentrically just as toe-off occurs, to drive the hip into further extension, as well as flexing the knee. This knee flexion motion is important as it lowers the moment of inertia, thus making it easier to swing the leg forwards. From its swing onwards, the hamstring works eccentrically to bring the knee into extension for heel strike. As shown above, the hamstring plays an important role, and that weakness in this muscle will not only affect the stride length due to the reduction in the hip extension, but also to the development of patellofemoral pain syndrome, as the quadriceps will now need to pull a higher increased flexed knee at stance. Henceforth, it is recommended that the athlete's hamstring strength is well conditioned for injury prevention measures. At the hip, Pandey et al. Study writes that the body center of mass accelerates outwards and downwards in the first half of the stance in response to the ground reaction force. The hip counters the downwards force initially through isometric contraction of the gluteus maximus and through eccentric contraction of the vastus muscles. As for the outwards force, the gluteus medius counters this through eccentric contraction. The gluteus medius being the only muscle counteracting the outwards motion, the strength of the gluteus medius plays an important role in the overall medial-lateral balance, to which the literature suggests that weakness in this muscle will result in an increased hip adduction angle that will increase stress on the lower limb and one's risk to the development of patellofemoral pain syndrome. Henceforth, it is recommended that the athlete's gluteus medius strength is well conditioned for injury prevention measures. Like the knee and the foot, the hip, as a resultant of the motions from the joints below, also moves in the transverse and frontal plane. The hip initially moves into internal rotation at foot strike to attenuate the impact force. Though the internal rotation at the hip is small, as the pelvis of the contralateral side translates anteriorly, brings the ipsilateral hip into external rotation. By the 20% mark of the stance, the hip undergoes through external rotation through to the remainder of the stance. The gluteus medius works concentrically in this part. In the second half of the stance, with the hamstrings assisting, the gluteus maximus contracts concentrically for the hip to undergo extension. The hip flexors then work concentrically in bringing the hip into flexion for swing. The hip also internally rotates throughout the swing through isometric contraction of the gluteus medius in preparation for force absorption at initial contact. To maximize running efficiency, the upper body serves to counterbalance leg movement and aids in raising and lowering the body center of gravity during the run. Specifically, during the stance phase, the contralateral shoulder depresses and protracts, while the ipsilateral shoulder retracts and elevates. This movement pattern is essential for opposing the inferior and posterior rotation tilts of the pelvis that occurs during the phase of the running gait. By coordinating these movements, the upper body plays a critical role in optimizing running performance. The spine, during the run, stays stationary and is inclined at 7 degrees of flexion. It is theorized that the flexed posture reduces knee load and increases hip and ankle loading. In this presentation, we have looked over the muscles involved in running and the musculoskeletal faults that can impede on performance. The presentation also examined the non-motor factors that can also affect the athlete's performance. Overall, I hope that this presentation has highlighted the fact that the non-motor components are as important as the motor components in the optimization of the athlete's performance.